All right, so chapter 5, section 1 is an introduction to random variables and probability distributions. This first slide is going to have some vocabulary words. I'll let you know the last two words are the most important ones. That's the discrete random variable and the continuous random variable. The first two just kind of set those up. First word being a statistical experiment or observation. We already know what that is. It's when something happens and we record information based off of it, but any process by which measurements are obtained. So before we can have a distribution, we have to collect data. Once we have the data, then we can analyze it, have a mean and a standard deviation. Once we know what to expect, we can use that information to come up with the probability of something else happening. Because in statistics, we can never say definitively what will not happen. We can just say with a certain amount of certainty the probability of it happening. Even if you say there's a 99% chance of it happening, if it were to happen, then you're pretty sure about it, but it could also not happen. You're like, well, I didn't say it was definitely going to happen. I mean, even with the COVID vaccines, my wife got the Johnson & Johnson's and she's saying how she's fully vaccinated, has nothing to worry about. I'm like, yeah, but it's only 75% effective. Like there's still a 25% chance that you could catch COVID. And same thing with the Pfizer, it's 95% effective. So there's still a 5% chance that I could still catch COVID. So there's still these probabilities that even though they have a higher immunity, there's still a chance. And anyway, with random variables, we usually record the variable as x. So when I have the formulas, I'm going to write p of x. That's the probability of that random variable occurring. And it's the variable whose possible outcomes are numerical outcomes, and it's of a random phenomenon. A phenomenon is just an event. So we are going to have variables usually as x, and they're just the outcomes of something happening. Now, the two words that are going to be important, and we're going to use these words on the first two problems in the homework. The first is a discrete random variable. So if something is discrete, that means we can count it. So my definition is when the observation of a quantitative random variable can only take on a finite number of values or a countable number of values. So the people in this room, the people that are remote, those are discrete variables because I can say there are 13 people, there are 4 people, I can count them. There's no debating and saying, well, technically, I think there's 13 and a half people. That's not a thing. So the fact that we can actually count it, that makes it discrete. A continuous random variable, think about the measurement being continuous as in you can always get more exact. So when the observation of a quantitative random variable can take on any of the countless number of values in a line interval. Something like height, you're 6 feet tall. Well, maybe you're 6 feet and 1 inch. Maybe you're 6 feet 1.5 inches. Maybe you get into centimeters. Maybe you get into millimeters. You can always get more and more exact with how tall you are because you can have a more and more exact measurement. Something like weight and distances, you can always have a more exact measurement. So a continuous random variable is something that you can always become more exact. If I said there are 13 people in the room, there are no other ways to say that other than just counting the people. You can't get more technical with the number of people in this room. And then obviously the examples that I gave for the two of them just kind of reiterate discrete versus continuous. So as I said, the first two questions on your homework is going to be just a list of events, and then you just have to say whether it's discrete or continuous. Now, a probability distribution. It's an assignment of probabilities to a specific value of a random variable or to a range of values of the random variable. So basically what this is saying is that something has happened and you've collected information and you have the expected probability of something happening. So maybe I've recorded over the last 12 years every single grade in statistics, and I can say that of all the students that take statistics, 75% of them get an A, 20% get a B, 5% get a C, things like that. So based off of information that I've collected, I can assign probabilities to certain outcomes. An A, a B, and a C could be the outcomes. Those would be my variables. And then the probability of them occurring would be what I've collected. So in this probability distribution, you are going to have a table of values. You are going to have certain events that have happened and the recorded probabilities of them already occurring. Based off that information, we can then use it to say, well, what is the expected number of B's? What is the expected number of A's? What's the probability of getting an A or a B? So we're going to use some of the probability information from chapter 4 that we learned and apply it to a more broader kind of holistic problem. Just some features of a probability distribution. It has a probability assigned to each value of the random variable. And you know that it is an appropriate distribution or a legitimate distribution if all the probabilities add up to 1. So if you're doing a probability distribution, you add them up and they add up to 90%, it wouldn't be a valid distribution because you're missing 10% of the information. So on the homework, they may ask, can we assume that this distribution is valid? And the answer is yes, because all the probabilities add up to 1. As we get into different distributions, there's different ways to test the validity of the probability distribution. Because if it's binomial, we'll have a certain requirement, and then if it meets that requirement, then it's valid. Geometric has its own, so on and so forth. If you were to graph a probability distribution, you would most likely use a histogram or a bar graph, and it would just show, here's the outcome, there's the probability of it occurring. So that's just kind of the features and visual of how we would graph a probability distribution. All of these distributions we're going to find are going to be more discrete, because if we say that the outcome is 5, then 5 is the only outcome we're talking about. What we're going to eventually do is go from discrete distributions to continuous distributions so we can pick any value. So all of chapter 5 is really working with discrete values, and then we're going to show we can transition into chapter 6, which will be more continuous variables. The formulas, and these are ones that we're going to need to do on Google Sheets. We've already seen ones like this. Hopefully it rings a bell, but at this point, I think it's been about 3, if not 4 weeks since you've used them. So if you don't recognize them, no worries. Also, if maybe you didn't do the assignments when we did this stuff, maybe doing it now would make it easier to go back and then fill in those holes of missing assignments. But these are the mean and the standard deviations of a probability distribution. And I wrote in there that's the mean and the standard deviation of a discrete population. So these are when we know the concrete outputs and there isn't another way of interpreting the variable. Now the first formula is, that is the Greek symbol mu. Again, that is for a population mean. And the only reason why it's a population is just because in the formula up here saying it was for a discrete population. We're going to take every output and multiply it by the probability of that output occurring. Do that with every single output and then add them together. So if we had the outputs of like 0, 1, and 2, and they had their probabilities, we would do 0 times its probability, plus 1 times its probability, plus 2 times its probability, and then we add them all together, and the outcome would be the expected number of whatever. The standard deviation, this is when we have to already have the mean, and we do every x value minus the mean squared times the probability of each x value, add them all together, and then take the square root of that. So the standard deviation we're going to have to do in 2 columns. And I have had some people reach out to me saying that they don't want to use Google Sheets, that they find it too frustrating. So if you are one of those people, hopefully being in person, we can start to iron out some of those details. but people did ask if they could just do it by hand. And I said, yes, it's going to be a lot harder, especially when we get into future chapters. You're going to have to use the tables in the back of the book, and it's going to be more estimating, whereas you could just type a command into Google Sheets. But if you were one of those people that want to do it by hand, I can obviously help out with that. It's your choice, and I'll accept both answers. But all right, so that's the end of the notes. I now want to just show you a couple of examples just so you can get an idea of how it would look going through the process. And then I will give you guys the rest of the time to work on the 4 problems and anything else that you need to do. So you should have access to this Google Sheet. I'll give people just a few minutes or a few moments, I guess. If they wanted to go in and steal a copy of it beforehand, you can, or you can wait till after, or you can just not and look at it whenever you want. But I'll just give people a moment for those that want to use it to do so. All right, so this was just a made up example. The values, which will be my variables, the X values, are 2, 3, 4, 5, 6, and 7. So there's no content behind them. But associated with each of the values is the probability of that variable occurring. So there's a 42% chance that 2 happened, 23% chance that 3 happened, 21% chance that 4 happened, 10% that 5 happened, 3 to 6, 1 for 7. So the first thing I'm going to do, just to make sure that it is valid, I'm going to do the command equals sum. And then I'm going to highlight this column just to make sure that equals 100%. And it does. So this is a valid distribution. Everything's accounted for. There are no gaps. We're not over 100%, not under. We are free to then go ahead and try this problem. So for the mean, I want to take every X value and multiply it by its probability, and then add all those products together. So I am going to start off with the command of sum, and then I'm take every X value. Actually, no. Let's break it up into 2 parts. Let's do the X value times the probability of it occurring. And now it's going to suggest that I autofill. You can click yes. If you did not, you can always click on the cell, grab the blue block, and drag it down. So those are kind of the 2 ways. Either it'll prompt you to autofill. If it doesn't, I don't know if yours will automatically prompt or if it just is used to me populating that it did. Google's sometimes intuitive with what you do. Other times they do updates and they don't let you know. So now I have all the products of the mean. And so now I'm going to do the sum of that column. And again, it's already prompting me, but I just want to go ahead and highlight. So I have that the expected output would be 3.12. Now, the first thing you should do is just kind of reflect of, does that make sense? Now, looking at the probability distribution, 2 had the highest probability, followed by 3, and then 4. So I'm expecting this to be between 2 and 4 for the expected value. Obviously, having 5, 6, and 7 is going to skew the values a little bit. But the expected output is 3, which kind of makes sense because you have almost half the values below it and the other half at or above it. And again, to find that mean, I multiplied every X value by its probability, and then I added that column up. Now for the standard deviation, I'm going to do this in 2 steps. The first step is going to be the x minus the mean squared times the probability of x. And then once I have that column, I am going to add the column up and take the square root of it. So in the first column will be the x minus the mean squared times the probability of x. And then the second column will be finishing off the square root. So again, start off with that equal sign. And I'm going to do my x value minus. Now, I had warned you with this, and some people were still using the value. I cannot click on the mean to use the mean. If I go ahead and I click on the mean to use the mean, I'm not done with the formula, I just want to show you, and I were to click and drag, what's happening is that I am getting some errors here. Because what is happening is that as I go down, and I've just populated it, notice on how I'm using cell C8. C8 is where the mean is located. As soon as I go down a cell, it's now going down to the cell below my mean. So in my next cell, it's taking nothing. It's subtracting nothing from my x value. When I go down again, it's now going down to C10. Once again, it's subtracting nothing. And then when I go down to the next cell, it's now trying to subtract the word mean from my x value. And Google Sheets says, I can't do that. So that's why it's giving me an error. So when you get your formula, you can't click on the cell where the mean is found because Google Sheets is stupid and doesn't understand that you want to stay in that cell. So I'm going to manually type in an approximation to this number. I'm noticing that it's stopping, it's terminating at 2, so I'm going to use 3.12. If you have something ridiculous that's 6 or 7 decimals long, just round it to the nearest hundredths place. I'll see that you're doing the right thing. I'm fine with it not being exact. So again, every value minus the mean, I'm going to type 3.12. That's now a constant. So when I grab that blue square and bring it down, it knows that it's using 3.12 in every calculation. Close that parenthesis, and I'm going to square it. So again, that is, for me, it's the shift 6. So it's that little caret symbol. Squared. Times, and now I'm going to click on the probability cell because when I populate it, when I autofill it, I want it to go down to the next cells of the probabilities and the values. So these ones, I do want them to use all those cells. That's why I don't manually type in 0.42, because I want that after I've done this part and I click and drag it down, that it is also going to use the 3 and the 23%, the 4 and the 21%, the 5, etc. So now I'm going to click and drag, and I can even just double check that I'm using A2, 3.12, and B2. And then when I go down to cell D3, it's changing it to A3 and B3, A4 and B4, A5, B5, A6, B6, etc. So again, you want to use the actual value of the mean and then click on the cells for the X value and the probability. All right, so the part that I just did was the first part of the formula. So that was x minus the mean squared times the probability of x. My next step is I'm going to add all those values together and take the square root of it. So I guess I can just do it at the bottom of the column. I won't create a new one. I'm going to do equals SQRT is for the square root. And since I've already done the equal sign, I don't need to do another equal sign. So it knows that it's already doing a command. So I could type in every single command in Google in one cell. As long as I start off with the equal sign, it's going to try to do them all. And again, they're suggesting I do D2 to D7. So you could click on that, or if you don't trust it, you can say no and highlight it yourself. It's showing you what's kind of nice in orange, what you are selecting. And I have the square root of the sum of x minus the mean squared times p of x. Hit enter, and my standard deviation is 1.2. So just as a quick little recap on what those two values mean. The mean is your expected value. So based off of what had happened, you're expecting to have an output of 3.12, give or take about 1.2. So this allows us in statistics to give a range of successes so that we're not saying, yeah, 3.12 will be your outcome. We're going to give a range so that we have a greater chance of being right. That if we say that we subtract 1.2 from 3, we get about 1. And if we add 1.2 to 3, we get about 4.3. So we're covering 2, 3, and 4. So if we were to add these abilities together, that's covering 86% of the values. So if I say that our expected value is between 2 and 4, there's an 86% chance that I'm going to be right anyway. So is that really that useful? Well, no, especially if you want a more exact value, but it's not technically wrong. It's just a way to manipulate the values. Again, the mean, every x value times the probability of it happening, add them together, you get the mean. Standard deviation, you have to do every x value minus the mean squared times the probability, and then square root the sum. Any questions with that? Okay, I do have 3 more examples, but I'm not going to go through and do all 3 examples. I just want to do one more example, and then if people want more, then we can do more. If people want to try the homework, then we can do that. So I don't want to, again, I don't want to waste your time. And now that I can get more feedback from people, hopefully we can make this a little bit better. But I want to do example 2 right here, only because this is an example where they're giving us a range. And some of the problems may have ranges. And so what this is that this is, they're looking at Super Shoppers. It's a fictional store. And they recorded the income of the people that shop at this superstore. And so the first income range was between 5 and 15,000. The next range was between 16 and 25,000, 26 and 35,000, 36 and 45, etc. Now you'll notice that the last output is 56 or more, because that also happens in statistics that it at some point it doesn't make sense to have all these outliers because maybe the probability would be below 1 and you don't really want to use that. So, and you'll notice that only 8% of these super shoppers have an income that's 56,000 or more. They could be making 56,000, could be multi-millionaires for whatever reason. They have a widespread. They're shopping at the superstore. So we have to adjust for the fact that this range doesn't have an end. Now, in order to use the mean and the standard deviation, we have to have a discrete value. We have to have an x value that we use as an output and then the probability of that output occurring. Now, the table would have given me this range and it would have given me the probability of things happening. I'm trying to find the mean and the standard deviation. So before I calculate the mean, I have to have a point estimate for each range. And that point estimate will be the midpoint. So I want to find the midpoint between 5 and 15. Now I had recommended that, and you may just be able to look at it and know immediately what it is, but maybe you want to have a nice command to do this for you. What you can do is you can find the average of the 2 values. So we're adding them together and dividing by 2. Google has that command. We can just type in the word average and then click and drag of the average from 5 to 15. And you'll see that it is indeed 10. It's asking to autofill, I'll say yes. Now, the only one that we have to adjust is going to be this last row because 56 is not the appropriate point estimate. Instead, I'm going to follow the pattern of what Google Sheets is doing. If they said that 10 is our first and then 20.5 is the next and 30.5, 40.5, 50.5, it looks like they are increasing by 10. So I'm going to make 60.5 be my point for the last one. So just follow the pattern to finish off for your midpoint. Now that I have point estimates for each one, I can now go ahead and do the mean. Start off with my equal sign. I am going to do my x value, which is the midpoint, multiplied by the probability. Now you'll also notice that I'm using the decimal equivalent for the probabilities. If you didn't, then you'd have to divide by 100 at some point, and it just complicates things. So I would just use the decimal equivalent. I won't autofill. Click, grab that blue square, drag it down. All right, so those are all the x values times the probability of x occurring. So now I am going to add that column together. Autofill, no thank you. So this is saying that the expected income for a super shopper is around $32,695. Give or take how much? Well, equals, parenthesis, my x value, minus, again, I'm not going to click on the mean because it will use all the other cells. So I'm just going to use the digits I have, square it, and multiply it by the probability. Not going to autofill because they want to fill in more than I want them to. So now I have all of the x values minus the mean squared times their probabilities and equals the square root of the sum of the cells I want. So this standard deviation is pretty high. They're saying that you should expect a super shopper to have an annual income of around 33,000, give or take 16,000. So again, within one standard deviation, you're having a huge spread of information because you're going as low as 16,000 and as high as about 48, 49,000. Is that really useful? I mean, someone living off 16,000 versus 50,000, that's a pretty big gap. So it doesn't quite give a lot of information. We would prefer a smaller standard deviation, but again, that's just what it is. But that is what we'll be doing today. The only thing that the book, I'm looking at some of the questions that they may ask, is they may ask what's the probability of an income being between 5 and 35,000. If a question like that's asked, you just add the probabilities together. So there is no extensive way of finding the probabilities. They just ask you in what range, and you just add those probabilities together. So if I wanted to know the probability between 5 and 35,000, I would just add these three probabilities together and get that there's a 57% chance that a shopper would be between 5 and 35,000.